so good afternoon, everybody. Welcome to this session on e-waste management in Africa. Actually, this is session 2J. I'm Harisios Achillas. I'm an associate professor at the International Hellenic University in Thessaloniki, Greece, and my focus is mostly on circular economy and reverse logistics. So today we have 6 presentations. In this session, we have 6 presentations. The session will be split into 2 slots. Actually, the setup is to have 3 presentations from Mr. Dofia, Zileni, and Vukt in the first slot. All presenters will have 8 minutes for their presentation, so please try to keep the time in your presentation. Then this will be followed by 2 minutes for Q&A if there are any questions on for some clarifications on the presentation. Then we will have a discussion about the 3 presentations altogether, and we will hopefully we will have 15 minutes for that, and we will move on to the second slot with another 3 presentations by Mr. RJ, Dominic Vukt, and Larry Kotoe. So I will not. Time is really flying. I will try to be to save some time for discussion at the end of the session of the slots. So I will immediately give the floor to the first presentation. Thank you all for your participation and your engagement to this conference, to this very interesting, with your very interesting presentations. So the first presenter will be Mr. Prosper Dofia from the Mountain Research Institute in Ghana, and the topic of the presentation will be sustainable e-waste manual dismantling through the operation of the Technical Training Center in Ghana. So Prosper, the floor is yours.
Sorry, I'm seeing that Mr. Dofia is not connected yet, or is he online?
Yes,
okay.
I'm connected.
Okay.
I guess you can hear me clearly.
Yes.
Yes. So will you moderate from your end?
I will. Do you want me to control the presentation, or if you want to control it, I can give you the control of the screen?
Yes, you can control it from your end.
Okay, perfect.
Yes. Okay. Thank you very much for joining this session. As mentioned earlier, my name is Prosper Dofia from Ghana with the Mountain Research Institute. I'll be presenting on the title Training on Sustainable E-Waste Management in Ghana, and just a background and introduction to the whole activity. So in Ghana, a huge volume of the e-waste generated in the country are primarily collected by the informal scrap dealers or workers. These individuals often lack necessary skills and resources for proper waste management. So consequently, they resort to improper dismantling methods and the retrieval of valuable components. Please, you can go to the next slide as I continue. Okay, thank you very much. So these informal guys resort to improper dismantling methods and the retrieval of valuable components, resulting in negative environment and health impacts. One notorious example of such informal activities was what was happening on the old Fardama scrapyard, which is commonly known as Agbogloshi worldwide. So recognizing the urgency of the situation, there are rules and need for formalization and capacity building within this sector. In response, the German Ministry of Economic Cooperation and Development, that's the BMZ e-waste program, developed a training concept in 2019. The goal was to promote environmentally friendly practices and enhance sustainable informal e-waste processing in Ghana. Yeah. So next slide. So this initiative led to the Ministry of Environment, Science, Technology, and Innovation, which is the mother ministry, to provide an old facility which was then renovated into a technical training center for this purpose. And as part of this effort, 21 trainers were trained to support the pilot and the operational phase of the program. You know, the primary objective of this assignment was to conduct technical training sessions on the proper management of e-waste. This was achieved through collaboration between GIZ e-waste program, the mother organization, which is MESTI, and the consortium, that is OCO Institute and Mountain Research Institute. So out of these 2,000 scrap workers were trained on proper dismantling and handling of this electronic waste. Next slide. Okay, so these are some of the purpose of the training. We looked at environmental awareness and health and safety. We also looked at how to handle some hazardous fractions which are within these electronic devices. And we also look at another aspect. We know these wastes are resources, and if they are resources, if these resources are supposed to be recovered, they have to be recovered very well. And we also look at some policy legislation with the mother institution, EPA, and then the MMDs that are also involved. Then we look at responsible recycling and disposal, and also at least promoting decent jobs, since that is what they are looking up to. And then this has led them to develop strategies or new processes of handling these devices for their livelihoods. Next slide. Okay, so this is an overview of the training models used at the Technical Training Center. We looked at a classroom session where the participants were taken through what electronic waste are, even though they already know what these devices are. We also looked at the health impact of improper handling, because that is what they are involved in. And then we take them through what they are supposed to do in order to avoid all this impact, both on the environment and also they themselves as the workers on site. And then we look at also introducing them to business registration and formalization processes. You know, in Ghana here with the informal sector, with their business registration and also formalizing them, they don't see it as an important aspect. So we also try to conscientize them and then highlight some opportunities and benefits they get from formalizing or registering their businesses. Then we look at the important aspect of the training, which is the dismantling sessions, which is the practical session, of which we take these participants through basic health and safety information that is helping them how to put on PPEs, the benefits of putting on PPEs, because on the scrapyard, these things are not seen and then they don't see it important. So we also highlight the importance of putting on these PPEs and also first aid for their use. And then we also look at the hands-on practical session where we demonstrate to them how these electronic devices should be dismantled properly, and then wearing safety boots and wearing other safety gears before participating in the exercise. We also take them through some downstream options, especially with the fractions that we get, those that are hazardous, how they are supposed to handle them, and those that are not hazardous, how they are supposed to handle them in terms of the downstream options for them, and also the recycling processes that are available for these fractions. And then we also look at the proper storage and disposal, because on the scrapyard, what these informal scrapyard dealers do is once they dismantle a device, they take out the valuables and then they discard the negative fractions, which is very dangerous to the environment. Next slide, please. Okay, so the e-waste trainer, who is made up of over 40 trainers who, as at now, who have undergone training of trainers. from the onset of the entire program. These trainers are made up of some personnel who have master's degree per their qualification, and then others who are also experienced in the scrap work, which really facilitates the whole work due to the experiences some of these scrap dealers have, and bringing them on board really helps. So this is just a structure and an overview of how the trainer pool look like. So we have a lead trainer, a co-facilitator, and technical assistants, where they all have their designated role for facilitating the whole training process. Next slide. Okay, so these are some of the training methodologies we adopted for carrying out trainings at the Technical Training Center. Some of these scrap dealers we deal with are adults, and we adopted an adult educational approach to assist in the whole process, so as for them to be able to understand well what we are trying to communicate to them. And on my right, this is just one of the workshops that was providing participants hands-on experience on e-waste segregation, the collection, dismantling, and the labeling. Then we also look at a workshop setting that we usually prepare for the dismantling session. Next slide. Okay, so in 2021, the scrap yard, that is the main hub where these activities were taking place, was demolished. These scrap workers were evicted from the yard, which really affected over 6,000 scrap dealers. Along with that, their economic activities were decentralized and spread across the region. The training program, please come again.
Please turn off your microphones, the rest apart from the presenter, and Prosper, please try to sum up because we are running out of time. Thank you.
Okay, so the training program recalibrated each training model to suit the new reality of what was on the ground, because these scrap dealers were scattered across the region. So we need to re-strategize our plans to meet the current need. Next slide. Yeah, so we brought up a new model, which is the mobile training, that is taking the trainings to their hotspot where they are located, and then also training them just like what we do at the Technical Training Center. But here we take the training to their designated location, so we'll be able to carry out our training activity. So these are some of the outcomes. And then the lessons learned from the entire program. Some of the scrap dealers have started registering their businesses, and then some have also going into these upcycling businesses, and they have also recognized some of the value of the fractions that they were discarding. They realized they could use it for other purposes, and also this has also helped in reducing the impact on the environment. Some of the lessons learned we realized training of the informal scrap dealer is really crucial for a sustainable management of e-waste, because they are really into the business and they are really on the ground dismantling these devices just for livelihood, and they need capacity building in such areas. And then we realize if there are strong scrap dealers association, it will really assist in the whole process nationwide and other areas as well. And regular engagement also help, and also ministerial support and collaboration was also one key point that helped in facilitating this entire activities. Next slide. Yeah, so that is that. I'll leave it here if there are questions or submissions, and then I look forward to that. Thank you very much for the time.
Thank you, Prosper, for this very interesting initiative and for your presentation. I don't know if there is any question, clarification question, not for discussion, but only for if someone needs some clarification from Prosper. If not, we should immediately jump to the second presentations, which will be delivered by Mr. Thokozani Zileni. from the University of Johannesburg and EMPA in Switzerland. Sorry if I pronounced your email wrong, Tokozani. The title of the presentation is Investigating Sustainable Options for End-of-Life Lithium-ion Batteries in the South African Context. Before I leave the floor to Tokozani, I sent also in the chat the link where you can vote for your preferred presentation of the session. So, Tokozani, the floor is yours. I don't know if you will handle or if it will be from Federico.
Tokozani, please, if you want to control the screen yourself, I can give you the control of the screen, or I can just move the slide at your orders.
Yeah, I'll move the slide.
Okay. You should be able to move it now if you want to try.
Am I audible? Okay. Please control the slide for me. I'm having network issues. There's load shedding.
There is some noise from you, Tokozani. Now your microphone is mute. Please turn on your microphone.
Okay, can you please take me to the first slide? Hello?
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 Are you not able to share the screen? Okay, I will move it at your order if it's okay.
Yes, please, Federico. Yes.
Okay.
Hello?
Hello. Yes, we can hear you. Clear now.
Am I audible?
Yes, Tokozani, we hear you. Okay.
Hello?
Yes, we can hear you. We can hear you.
Okay. Okay, I'll start. Sorry, I'm having there's load shedding and network, and the school's Wi-Fi is messed up. Good afternoon, everyone. I will be talking about sustainable options of dealing with end-of-life lithium-ion batteries in the South African context. Well, for background purposes, South Africa is in a crisis in terms of lithium-ion batteries, since they are very hazardous for the environment, and the country, most people usually discard of their end-of-life devices in their dustbins, so these batteries end up in landfills where they pollute or contaminate the soil. So for my thesis, we thought we should look at sustainable options that we can explore in terms of dealing with this end-of-life waste. And one of our themes is state of health estimation. Can I please be taken to the next slide? So in state of health, basically state of health estimation, is like being a battery doctor and you get to test how much lifespan the battery has left. So generally in state of health analysis, you've got two methods, experiment-based and model-based. Model-based methods are usually for electric vehicles and are for real-time applications. Then you have experiment-based methods, which are the route that I chose for my thesis, which are, please, next, please, which are conducted in lab conditions. Next, and with the use of an eye charger for my thesis, as we calculated the remaining capacity of the batteries and the increase of internal resistance. Can I please take me to the next slide? So with capacity is usually the general indicator for state of health of a battery used by multiple companies. Apple, there's a company here, Revolve, for their energy storage system. They use capacity keyboards in Switzerland, Upvolt in Switzerland. So generally in industry and in literature, that's the parameter that is used. So with the eye charger, as you can see in the picture, because this is all meant to be integrated into the informal sector. So we used an eye charger, which we can say is somewhat affordable for a technology station. So it's about 200 to 300 francs, so about 8,000 rands. And with it, we took old batteries. We ran tests on old batteries from cell phones, laptops, e-bikes, and one EV, but is not included in the study, just to run capacity test and internal resistance. Can I please take me to the next slide? Can I have the next slide? Next slide, please. Can I have the next slide? So the eye charger, as seen in the previous picture, calculates internal resistance, as seen in the diagram, and capacity during charge and discharge cycles. I was accompanied or guided by an electrical engineer. As a geographer, I had 4 months in Switzerland to learn this. So we are assumed that since as a geographer, we know any scientific knowledge background, and having to learn this in 4 months, it can be applied to for the informal sector waste pickers. So it's very simple. You plug the cells into the eye charger, and through a charge cycle, it calculates capacity, as seen in the right, and internal resistance. Can I have the next slide? So and we had a laptop, battery, 2 e-bikes, a power bank, and a drone. And these are the results that we obtained. So you're connected in the eye charger, analyzes cells that are connected in series. So we had to make battery packs in series, and you can after that column you can see the beginning of life capacity. Then you find the measured capacity given by the eye charger. Then that gives us the state of health expressed in percentages, which, as I mentioned, generally in industry or in literature, this is the method used to calculate capacity, because it's so simple. With it, we can activate the value chain of the informal sector by offering this tool that is easy to apply, and it won't bring a whole brand new wide spectrum light, but it's a step towards the right direction, because people can estimate. The waste pickers, when they get this batteries from dustbins, they can at least estimate the state of health. Then you reuse some of these batteries and some be sent to recycling. So it's a parameter that can somewhat control the end of life value chain in South Africa, especially with the informal sector, which includes waste pickers and repair shops, and they're found in malls and different economic centers across the country. Can I have the next slide? So to conclude, there are existing state-of-the-art technologies in the country, but found in the formal sector, like I mentioned, Revolve, which is an energy storage system company. They basically import end-of-life lithium-ion batteries from China, which are used in buses, electric buses. Then when the batteries get this side, they reuse the battery for energy storage systems. And you also find ESGS software by Apple, which they use capacity to determine how healthy the cell is. And there is Rec Light, which uses capacity and also checks the external damage of the cell and the temperatures, age to determine how healthy the cell is. And there is also SGS, which is a Swiss company. They state-of-health analysis for electrical vehicles, but the electrical vehicle market is just started in South Africa, so they are not as well known or solid as the others that I have mentioned. Then we have there is potential of actually activating the informal lithium-ion battery value chain in South Africa, especially with implementation or the provision of tools like a state-of-health protocol or assessment tool like the one developed in my thesis. But we also find challenges like cost, because an iCharge is about 9,000 rands. It's affordable to some extent for a technology station, but actually it's quite expensive for informal waste pickers or repair shops. So that it would bring us to the challenges or potentials of scaling and implementation. One iCharger can only analyze 20 cells at a time, and it will take us a day or two to finish 20 cells. So perhaps we'll need more iChargers in order to scale it and have workshops in order to activate and enable waste pickers to actually do something about end-of-life lithium-ion batteries in their waste value chain. Thank you. That's the end of my presentation.
Thank you, Fokozani. Thank you for this very interesting presentation. I don't know if there is any question for clarification. I don't see anything in chat. Okay, so maybe we should move to the third presentation and open the floor for some discussion. The third presentation will be delivered by Dominique Vogt from Stellenbosch University in South Africa, and the topic of the work is material flow analysis of the recycling of lithium-ion batteries in South Africa, collection, processing, and product distribution. Dominique, you have 8 minutes for this presentation.
Thank you very much. Good afternoon, everyone. My name is Dominique Vogt, and today I'll be speaking about the research I've done, which I have titled The Material Flow Analysis of the Recycling of Lithium-Ion Batteries in South Africa. I'll be focusing on the stages of collection, processing, and product distribution. Next slide, please. So just the background and aim of the work that I've done. So there's an increasingly large stream of lithium-ion battery waste expected in South Africa. Approximately 3,000 tons of lithium-ion batteries will become available for recycling in 2023, and this will just increase year on year. There's no legislation to mandate specifically the collection or recycling activities of these batteries once they reach end of life in South Africa. And additionally, there are no lithium-ion battery waste processing facilities in South Africa or on the African continent. So as a result, the end-of-life lithium-ion batteries in South Africa are either disposed of illegally, stockpiled, or they are exported. So the aim of this investigation is to analyze a theoretical reverse logistics network or recycling network for the recycling of these batteries in South Africa. And then we perform a material flow analysis so we can determine the feasibility of these recycling networks, and then to give recommendations on the way forward for the recycling industry in South Africa. Next slide, please. Next slide, please. Thank you very much. So here we have an overview schematic of the recycling network with our system boundaries from an MFA perspective. So First off, on the left, we have our collection centers. This is where we collect end-of-life lithium-ion batteries present in electric mobility applications, as well as e-waste. The material then goes to disassembly facilities, where we remove the batteries from devices, and the resulting material would then go to the e-waste recycling industry in South Africa. The batteries would then go to end-of-life lithium-ion battery processing, where we utilize mechanical pretreatment as well as hydrometallurgical processing to process these batteries, and then we produce end products which go to both international and local customers. These end products we produce are cathode precursors, which can directly go into making new batteries once again. So it is, in essence, a closed loop system or a circular economy. Next slide, please. So here we have the experimental scenarios of this investigation. So we looked at two main processing routes. The first route is an inorganic process route where we utilize hydrochloric acid to leach our end-of-life batteries. And the second route looks at an organic route where we utilize citric acid. For each of these routes, we are producing two main product types. MP refers to metal powder precipitates, like nickel hydroxide, cobalt hydroxide, etc. And NMC refers to an NMC hydroxide or phosphate precipitate, which can be reused to synthesize cathodes. We have three different process configurations for each of these product types. SFNS refers to a single process facility which is not scaled up. So that's able to meet the average demand of end-of-life libs in South Africa. SFSU refers to a single facility which is scaled up, and that is able to meet the full demand of waste in South Africa. And MF refers to opening up multiple facilities so that we can utilize the full demand. And that is a total of 12 scenarios. Next slide, please. So for each of these 12 scenarios that I have described, we perform MFAs in both STAN and in eSankey, and we perform three main types of MFAs. So first, we perform a material flow analysis over the entire recycling network. So this allows us to track the flow and the fate of end-of-life libs, of e-waste, and our final saleable products. Then we perform an MFA over the process facility itself, so we can track the flow of black mass, of raw materials, waste that we produce, and the products that we produce. And then I perform an elemental flow analysis over the process facility. And this allows us to track the flow and the fate of our metals of interest, which are cobalt, lithium, nickel, and manganese, through pre-treatment and processing. And this just allows us to make a very comprehensive analysis and informed decision-making on the way forward. Next slide, please. So key results. So this is from the initial flow analysis. So what we see here is we see end-of-life lithium-ion battery flow rates for various strategies of collection from 2021 to 2022 to 2033. So here in green, we have an optimistic strategy. And with this strategy, an end-of-life process plant is feasible in 2023. For a pessimistic strategy, an end-of-life process plant becomes available only in 2027. And at the current collection rate, which is approximately 1%, an end-of-life battery process plant is infeasible. So what this shows us is how sensitive the recycling industry is to the rate of collection of material, and it shows us that urgent action is required in terms of legislation and regulatory action. Next slide, please. What we have here is we have the end-of-life lithium-ion battery flow rate breakdown for consumer electronics on the left and for electric mobility applications on the right from 2021 to 2033. And the main conclusion here is that the majority of end-of-life lithium-ion batteries in South Africa are expected to come from consumer electronics rather than electric mobility applications. And this needs to be considered when incorporating further legislation or developing infrastructure. Next slide, please. So what we have here is we have the material flow analysis done in STAN over the entire recycling network. This goes through the phases of collection, dismantling, and processing. And what I would just like to draw your attention to on the left here is the substantial flow of material that comes from e-waste compared to the flow that would come from electric mobility applications. Next slide, please. Here we have an example of the material flow analysis over the process facility. Here we can track the flow and the fate of materials through mechanical pretreatment and hydrometallurgical processing. And here I don't want to go into too much detail because of time restrictions, but here I would just like to draw your attention to the amount of reagents that are required to process and recycle these batteries compared to the black mass that enters the process, for example. We can also see the waste that we produce, the products that we produce as well. Next slide, please. Here we have the elemental flow analysis over the process facility, and here we can track the flow and the fate of cobalt, lithium, nickel, and manganese through mechanical pretreatment and hydrometallurgical processing. And what we can see here is that if we look at the recovered metals to final products, we can see that there is a very good recovery of cobalt, lithium, nickel, and manganese to our final products compared to the feed. So in general, we are seeing very good recoveries of our key metals of interest from our initial feedstock. Next slide, please. So just to summarize all the information, approximately only 3% of the material reports to end-of-life processing. This is just due to the substantial amount of e-waste that we need to obtain the lithium-ion batteries. And then again, this shows us that there is an integrated relationship required between the e-waste and the end-of-life lithium-ion battery recycling industries. In terms of raw material consumption, inorganic acid-based processes are preferred. In terms of total waste production, your organic acid-based processes produce less total waste. In terms of total saleable product production, inorganic acid-based processes are preferred. They have higher leaching efficiencies, and thus you produce more product. In terms of the recovery of your metals of interest, your inorganic acid-based processes are slightly better. And if we compare the average recovery, for example, for the HCl NMC process, we have an average recovery of 0.93 versus 0.89. Then from a circular economy perspective, inorganic acid-based processes are recommended as all the products can remain in the local market from 2028 to 2033, which promotes a circular economy between the recycling of end-of-life lithium-ion batteries and the production of new lithium-ion batteries. Next slide, please. So acknowledgements, I would just like to thank my supervisors and all those who contributed to the work that I have done. And next slide, please. And thank you for your time. I really appreciate it, and I appreciate being here, and I'm free for any questions.
Dominic, for keeping the time also, and also for your very nice presentation, very explanatory presentation. Okay, so this is the end of the first slot of this session. So we have some time for Q&A, for some questions, like 5 minutes, before we move on to the second slot of the next 3 presentations. I don't know if there is any questions from the audience. I don't see anything in chat, but if you want to ask any presenter or something, you may turn on your microphone and shoot it. Okay, if not, I have a couple of questions for first to Prosper Dorfia about the program, the training program. Is it still ongoing or has it ended? And what is the impact of in your view, what was the impact of this program?
Yes, so the training session, the training program is still ongoing. Currently, they are in phase 2 of the GIZ e-waste program, and the impact of this whole training is to give the scrap dealers basic hands-on practical dismantling sessions to at least understand better what they are doing, and then the hazardous nature of the devices that they are dealing with and how to properly manage them.
Okay, what is your vision after the training center? What is this a business opportunity also, or what?
Yeah, so as I mentioned, that some of these scrap dealers are also currently going to upcycling. They are turning some of the fractions into finished products for sales on market. And then the vision, as you mentioned, is to formalize the whole informal sector to also avoid their the practices that they are into, because we know what is happening with this sector, and then it is necessary to at least build their capacities in that line. So basically, it's to formalize the sector.
Thank you. Thanks a lot. I see there is a question, maybe more, I would say a clarification question to Dominic. So the question is, why do you say that there is no legislation to encourage the recycling of end-of-life batteries? There are VAP regulations which include them.
Yes, thank you. I just saw that question now. So I did not mention the EPR. I was more referring to specific legislation such as the Battery Directive, which has specific requirements for collection rates and recycling rates. So we do not have those in place, but we do have EPR in place.
Thank you. I don't know if there is any follow-up question on this. Okay, so I guess, Dominic, I understand that the most critical parameter is collection rate, right?
Yes, yeah. That is quite urgent in South Africa at the moment.
Yeah, so are there any incentives in South Africa towards public awareness, and how could you increase this rate? Are there any current initiatives?
There are a few. So there are a few initiatives from private companies. So, for example, one company, Macro, which is a very large store that sells sort of general products. They started with collection centers to try and collect e-waste, which I believe is quite it's going quite well. But in terms of awareness, and that I believe that is something which needs to come more from a governmental side. And that needs to be strengthened in South Africa, especially when it comes to collection. So we have a law in place, for example, that says that you may not dispose of end-of-life lithium-ion batteries to landfill, but I believe that more has to be done when it comes to collecting end-of-life lithium-ion batteries and e-waste to try and get those rates of collection a bit higher.
Thank you, Dominic. I don't see any other questions. So maybe, yeah, and it is already 2:45 CET, so maybe it's time to move on to the second slot, where we have 3 more presentations, and the first one will be delivered by Gladys Adjei from Ghana Atomic Energy Commission. And the topic of the presentation, the topic of the work, is separation and characterization of brominated flame retardants containing plastics from e-waste and assessment of disposal options for BFR plastics. Gladys, the floor is yours. We do not hear you, Gladys.
Hello.
We hear you with some echo. Because you have 2 microphones on. So now, can you try again?
Hello, can you hear me now?
Yeah, with some echo. I see you are connected with 2 accounts. So maybe now it would be better. Try again, once again, please. Gladys, if you can start your presentation. No, we cannot hear you with this account. Federico, do you think that we should move on to the next and allow some time for Gladys to rejoin with the other account?
Yes, I'm seeing Gladys connecting
Okay.
in another
Okay.
one.
All right.
Sorry.
Let's wait for a minute. It's okay.
Gladys, can we wait for you just a minute? Are you trying to connect or?
Yes, I'm trying to connect.
There we
So
go.
can you hear me now?
Yeah, that is better. Thank you.
Okay, thank you. So
Gladys, is there another computer playing the meeting near you? Maybe if you could silence that other computer.
Okay. So the topic of my presentation is concentration identification of coordinated gaming patterns from WRF containing plastics from e-waste and options for disposal and recycling of WRF plastic. Next slide, please. So what's a digital?
Gladys, we can hear you with
Yes, sadly we
difficulty.
cannot hear you properly. Maybe
No.
if we continue with other presentation until you can get a better arrangement of your computer, probably.
Okay, all right.
Okay.
Yes, please, Federico, yes.
Dominic, is it
Okay,
okay if you
yeah.
continue with your second presentation?
Thank you, Federico. So yes, we will have the next presentation also delivered by Dominic Vogt, and the topic is reverse logistics network optimization for the recycling of end-of-life lithium-ion batteries in South Africa.
Good afternoon, everyone. Thank you. Thank you for having me again. So I will speak about the next part of my research, which I've titled the reverse logistics network optimization for the recycling of end-of-life lithium-ion batteries in South Africa. Next slide. So just in terms of my background and aim, this is very similar to what I've shown before. So once again, there exists a need for sustainable recycling routes for end-of-life lithium-ion batteries. Approximately 3,000 tons will become available in 2023, which will just increase year on year. And there are no lithium-ion battery waste processing facilities in South Africa or on the African continent. So thus the aim of this investigation is to develop a theoretical reverse logistic network model or recycling model and determine the optimal reverse logistic network configuration for the processing and recycling of end-of-life lithium-ion batteries in South Africa. And we are focusing on it from both an economic and an environmental perspective. So we have these two modes in our optimization. This we achieve by material mapping, which I've just shown in the previous presentation, modeling and optimization. So from an economic perspective, we would want to maximize the profit or the economic feasibility of the reverse logistic network. So here we want to maximize net present value, and environmentally we want to minimize the environmental impact, and we are focusing primarily on minimizing CO2 emissions throughout the entire reverse logistic network. Next slide, please. So here is an overview schematic, a very basic overview schematic of the reverse logistic network. Once again, we have our collection centers. This is where we collect end-of-life lithium-ion batteries from e-waste and from electric mobility applications. That resultant material then goes to dismantlers. Here we remove the battery from the device. So for example, if it's a laptop, we remove the laptop, the battery from the laptop, and the resulting material would go to the e-waste recycling industry. These end-of-life libs then go to the process facility, where we utilize hydrometallurgical processing to process and recycle the batteries. and we produce end products which go to our international and our local customers. As I've mentioned before, these end products are cathode precursors, which can be used to produce new batteries. So there is a closed loop structure in place in essence. Next slide, please. So here is the methodology. So once again, we have the 12 scenarios. So we have two different process routes. The first route is an inorganic acid processing route where we utilize hydrochloric acid. And then we have an organic acid process route where we utilize citric acid. We then are producing two main product types. MP refers to metal powder precipitates like nickel hydroxide, cobalt hydroxide, etc. And NMC refers to either producing an NMC hydroxide or NMC phosphate. We then have three different process configurations in the network. So SFNS refers to a single facility which is not scaled up, and this is able to process the average demand of batteries for the network lifetime. SFSU refers to a single facility which is scaled up, and it is able to process the full demand of batteries for the network lifetime. And MF refers to opening up multiple facilities so that we can process the full demand of battery waste available. We then model and simulate these configurations. So there's 12 configurations. We model and simulate them in logistics for the period of 2023 to 2033. We then perform a combination of greenfield analysis and network optimization experiments. This allows us to determine the optimal location and number of facilities in the reverse logistic network. We can thus minimize transport distance and therefore cost, and we can minimize our CO2 emissions through the network. We also are able to determine the trade-off between fixed investment cost, transport cost, and CO2 emissions. And this allows us to determine the optimal network configuration from both an economic and environmental perspective. Next slide, please. So here is the network echelon structure for the optimal scenario. As an example, we can see here we have our collection centers, our dismantlers in blue. In red, we have our process facility, and then we have our ports, etc., for international distribution of product and local distribution of product. So our primary products, the NMC and lithium carbonate, that is exported to international markets for lithium-ion battery production up until 2027, but they can be kept in the local market from 2028 to 2033 for lithium-ion battery production. The secondary product, sodium chloride, that can be kept in the local market for chlor-alkali production for the full network lifespan. Next slide, please. And here is just a picture of the simulation diagram of this network. So this is actually what it looks like in theory. So in green here, we have our collection centers. There are 212 of these collection centers. So we determined the number and location of these collection centers by developing a collection center distribution model, which just chooses the optimal location for a collection center based on economic and social indicators. We then determined that in blue here, we have the dismantling facilities. So there are 9 optimally determined dismantling facilities. And then we have 1 end-of-life lithium-ion battery process facility, which is centralized according to those. Next slide, please. What we then did is we performed an economic analysis over each of these configurations. We performed a techno-economic analysis for a period of 20 years. Here we can see the net present value of each of these 12 scenarios. And what we can see here is that HCl NMC, so an inorganic acid-based approach, producing an NMC product, yields the highest NPV across all categories. However, this is purely from an economic perspective, and now we also have to consider the environmental perspective. Next slide, please. So if we have to consider the environmental perspective, what I did is I performed a carbon cost optimization. So I used carbon tax to determine the trade-off between CO2 emissions and NPV. And essentially, for example, if you have a much larger reverse logistic network, you have a much higher NPV, but the disadvantage is much higher CO2 emissions. If you have a smaller scale reverse logistic network, the disadvantage is lower NPV, but once again, the advantage is less CO2 emissions. So how do we find the trade-off between those two relationships? So what we do is we determine the net NPV after carbon emission cost. And we can see in this diagram here we have the objective net NPV taking into account the cost of carbon, the equivalent cost of carbon. And we can see here that SFSU, a single facility which is scaled up, is still the optimal configuration in South Africa. So thus, to conclude, we have determined that a single facility which is scaled up, utilizing an inorganic acid-based processing approach and producing an NMC-based product is the optimal configuration in South Africa for the way forward. Next slide, please. And then once again, I'd just like to thank my supervisors and all those who contributed to the project. And yes, thank you. And I'm free for any questions if there are any.
Thank you very much, Dominic. I don't know if there is any clarification question. Okay, so we will leave discussion for the end of the session. And it is time to move on to the next presenter, Mr. Larry Kotoe from the Environmental Protection Agency in Ghana. And the topic of the presentation is elaboration of an integrated e-waste management scheme for Ghana. So Larry, we can hear you. Please proceed.
Thank you. Yeah, good afternoon. Can I have control of the slides, please?
That's okay, Mr. Kotoe. Please try to move the slides. You should be able to.
I don't think it's working, so. Okay, so I'll proceed. So I don't think it's working, so let's go to the next slide, please.
Yes, I have given you the remote control, but it says it is waiting.
Oh, okay.
Are you not able to move the slide?
It's not moving, so.
Oh, okay.
Well, we can proceed.
Okay.
So my name is Larry Kotoe with the Environmental Protection Agency, and I will be presenting on the elaboration of an integrated e-waste management scheme for Ghana. Next slide, please. So I'll give a brief overview of the context for e-waste management in Ghana and also the regulatory tools that we are using. And then I'll go into the integrated e-waste management scheme itself. Next slide, please. So for the records, the amount touted agglomeration is no more what it used to be. So the old FADAMA that we used to know on the left of my slide is no more. And now that's how it looks on the right. So the discussion is a bit different and the dynamics are a bit different. But we must say that the value chain dynamics still remains something of priority for the agency and also for government in terms of the high informal activity when it comes to collection, dismantling, recovery, and even transportation. However, we've witnessed some fast entry of business to business when it comes to dismantling, and that's where our main focus are. Because the crude methods that are being used by the informal sector is what actually led to the pollution that we have observed over the years. So once we are seeing some fast entry of business to business and more formalized activities, that would be great. However, informal collection is still high and they have the expertise to do more collection. And I hope that they will still be integrated into the scheme. Next slide, please. So basically, we have the Environmental Protection Agency Act in terms of the regulatory tools that we use. And over the years, we have used the Environmental Assessment Regulation, which is the tool that we use for permitting of various undertakings. And it also includes e-waste activities, which is mainly the value chain activities. But from 2016, we witnessed a very transformative period where we enacted Act 917 and then the LI 2250, and it remains the foremost laws that regulates hazardous waste and also electronic waste in Ghana comprehensively. We also decided to enact the technical guidelines, and that is also to communicate the regulatory philosophy of the EPA to our, I would say, proponents or private sector in terms of how we want to regulate the sector. And this incorporates very unique activities that I'll be discussing in the next slides. But most importantly, also, the Act 917 introduced the Eco Levy, which is a bit novel because this is a levy that is being collected on all electronic equipment entering into Ghana, because Ghana is a net importer of electronic items. So this is supposed to be used for the recycling or the management of electronic waste in Ghana. And that is being collected since 2018 into a fund that is being managed by the e-waste fund. And that is something that is novel within our context of e-waste management. Now, the integrated scheme is how do we put together the informal sector and also our aspirations for incentive-based system and looking at provisions of EPR that has already been incorporated into the legal framework. And then also how do we track collection material flow along the chain in Ghana. And that is the next slide I'll be discussing. Next slide, please. So this is the scheme, and the scheme has components for take-back schemes and financing, which is the EPR, and it's already a part of the Act 917 and LI 2250, where producers or importers are supposed to take responsibility for their waste that are, or their product that are introduced onto the market. We also have a component for pricing, and the pricing component is where we are looking at how an incentive-based system could be used to motivate a lot of the collection of the hazardous fractions by the informal sector into formal recycling. So the pricing regime, how do we compensate or undertake an incentive-based system? So we are calculating how much we can pay for a ton or a kilo of a hazardous fraction. And that is something we have incorporated also within the scheme. The material flow, we are talking about mixed-use e-waste, positive and negative fractions, moving along the value chain of e-waste management in Ghana. How do we want to see it? Moving from one stage of the value chain actor to the next, all the way to disposal, which we have also provided. And then in all this, you need an infrastructure that is supposed to support all these activities that we want to undertake within the scheme. Next slide, please. So within the scheme, the first point of material collection is the tier 1, which is more of collectors and repair shops. So within the context of Ghana, we have collectors, and then also which is more of the informal, and then we have the repair shops. These are the foremost contact points for receiving any faulty or any waste that is coming from household or commercial sector in terms of e-waste generation. So these are the first point that we have. Next. The second compartment, which we have called the tier 2, and they are the collection centers and holding centers. And these are the centers that are supposed to be served or going to serve as buyback centers for incentive payment. So these are also collection points where once things are collected by collectors and also repair shops and other things, these are supposed to be handed over to the collection centers who are mandated to do a bit of sorting and all that within the integrated scheme. So we are linking the informal sector into the formal collection that they are not capable of doing. Next slide. Now we go into the pre-treatment, or what we call the depollution. Here we are also looking at dismantling, and here we are looking at also selective treatment and then further processing of these positive and negative fractions. And here we can be able to identify the positive fractions and the negative, and then also creating value addition for metal recovery or material recovery, and also disposal options. So these are the scheme areas that we are looking at within an integrated approach. Next slide, please. And then the last one, we are talking about energy recovery and also disposal. Now, when we pick each of the components one by one, next slide, please. When we pick each of the components one by one, here, when we talk about the collection centers, here we are looking at where e-waste will be sorted, and we have developed very detailed processes. And as you can see the pictures, these are real pictures that are ongoing in a typical collection center where e-waste is collected and sorted into the various categories. And these are the best practices that we want to also have on the ground for a typical collection center. So detailed processes has been developed for them at this level. Next slide. Now, when you move to the dismantling, this is where the depollution is very much important, and we have also developed detailed processes where we have been able to identify or categorize hazardous fractions, also pure metals, and also mixed fractions, as well as reusable components that is supposed to serve the repair shops or refurbishment industry to also try to close the loop. So there's a forward-looking model where we are actually developing detailed processes for some of these dismantling facilities. Next slide, please. Now, in terms of further processing, so from the dismantling facility, we are able to tell which of the hazardous fractions need attention. Which of the hazardous fractions need attention. Here we are talking about lead glasses and also ODS gases, and then also materials that are of value or also which are not of value. So these are also detailed processes that have been identified for further processing of negative fractions, which we have also developed within the value chain in Ghana now. Next slide, please. Now, I made mention of the availability of infrastructure to be able to implement this entire scheme. And having collection centers and also dismantling centers is also an area that we need to look at. Although we have private sector also having a very important role to play. The EPA, through the World Bank funded Africa Environmental Health and Pollution Management Project, we are constructing additional 5 centers, which we are calling the dismantling, collection and dismantling centers across the country. And these are also supposed to serve as the buyback centers for the payments of incentives. And these centers should be completed by next year to augment our integrated approach, whereby the livelihoods of the informal sector could be guaranteed, where payments could be made for some of the incentives for collection of specific hazardous fractions like lithium batteries and all that. So these are centers that are supposed to be finished construction and support the whole scheme by next year. Next slide, please. So in terms of the incentive-based payment that we are currently also undertaking, so we are doing a piloting of the incentive-based with the informal sector, specifically the collectors. And as we speak, we started in 2020 through a MEST-PIU project. And then we are now in 2023. And so far, we have rolled out the piloting of incentive-based collection, specifically for the informal sector, looking at cables, looking at mixed batteries, CRTs, thermoplastics. And these are materials that in Ghana, we have classified or categorized as the most problematic ones that have seen a lot of debate in terms of how their metal recovery has caused a lot of pollution. So these are the incentive-based system that we are currently implementing, and hopefully it will be transitioned onto the national scheme once we have learned a lot of lessons out of it. But the next slide, please. Now, one of the innovations that we have also introduced when it comes to the integration of the informal sector, because it is very important in terms of their livelihoods, and because we've also identified them to be a very good source of collection point. They will be very good also at the waste management end, and we know that the district assembly or the local assembly are where those are the levels where collection can effectively be done. So through the EPA, we are also collaborating through the assembly, where the scrap dealers are supposed to form associations. So now we have evidence, or we formed associations for some of these scrap dealers who have membership, over hundreds of them under each association. And our integrated scheme is looking the model where they can acquire some legitimacy to collect even to businesses and households. So now an ID card system has been introduced for some of these associations for their members, so that at least we can change their legitimacy in terms of how they can approach households and also businesses to collect some of these e-waste into the formal recycling chain. So our integrated approach is not to actually take away the informal sector, but actually to integrate them and also guarantee their livelihoods when it comes to the collection of hazardous fractions out of the environment. So in a nutshell, that is what the integrated scheme seeks to do, and also implement an EPR system that is forward-looking in terms of the future of circular economy. Next slide, please. Thank you very much. We do this with the EPA as the lead implementer, and then also our ministry, and then we have the cleaner production, and the mountain research is also key part of this collaboration, and also the two German corporations in Ghana. Thank you.
Thank you very much, Larry. This was very clear. I don't know if there is any question for Larry at this point. No, so maybe we should try once again to connect with Gladys. Gladys.
Hello.
Thank you. Okay, now we hear you clear.
Okay.
So Federico, if you could share your
Just a minute,
screen.
please. Just a minute.
Yeah.
Dear Gladys, can you see your presentation?
Yes, please.
Okay, so this is Gladys Ajay from Ghana Atomic Energy Commission, and the topic is separation and identification of BFR containing plastics from e-waste and options for disposal and recycling of BFR plastics. Okay, Gladys, please proceed.
Thank you very much. So my name is Gladys Ajay from Ghana Atomic Energy Commission. I'm presenting on the topic separation and identification of brominated flame retardants containing plastics from e-waste and the options for disposal and recycling of BFR plastics. Next slide, please. So with the upsurge of electronic equipment due to new equipment being produced for healthcare, education, communication, and other things, electrical and electronic equipment has led to the alarming influx of EEs in Ghana, which are mostly second-hand equipment. And this upsurge in Ghana has led to a high generation of plastics in the country. And at the end of their lifespan, these EE plastics are discarded. They become available for recycling and also for reuse. And then valorizing plastics fraction is challenging because the different plastic types needs to be sorted because some of the plastic contains hazardous chemicals. Next slide, please. So the electronic plastics that contains BFR are, however, processed in treatment plants without them being treated, which will have an impact and will affect plastics in using as a secondary resource. And also recycling may introduce BFRs or other hazardous chemicals into the plastics, leading to increased exposure levels in the environment and to human health. So the need for segregation and disposal reciprocity or debomination before recycling has become inevitable. So this study was to separate and identify BFR containing plastics from e-waste and as well as assessment of disposal and recycling options for BFR plastics. Next slide, please. So the method used was formulated by EMPA to identify different types of plastics from the e-waste plastics so that they can be separated well and recycled accordingly. So the first method that is used to identify plastics is by using a chemical lemoning. So that's the process that goes through with the lemoning on your left. And the resultant result is what is on your right. Next slide, please. So Second chemical used is acetone. This also gives a different characteristics of different plastics, and that's the method used to follow to give you the different type of plastics that you can identify from using the acetone. Next slide, please. Change my slide. So from using the acetone and the limonene, you get your different types of plastics, and this density test shows you the different types of plastics which are infused with BFR or which are not infused with BFR. So the container on your left on your screen shows plastic that has sunk in the salt water. And then the ones on your right shows plastics that are floating in salt water. So those that are floating do not contain BFRs, but those that have sunk in the salt water contains BFR. Next slide, please. So after all the testing, those plastics that do not react with acetone or limonene also goes through another test using fresh water to determine the other plastics that are not reacting with the limonene and then not reacting with the acetone. So those plastics that do not react with the acetone or the limonene will either be this flow chart, the results in the green colors over there. Next slide, please. So at the end of the separation of plastics, this separation of plastics was done in a recycling company which has dismantled electronic equipment, but they need plastics to be sorted out so that they can recycle them. So the total amount of electronic plastics that was worked on at the recycling facility was 5,701.4 kilograms. And of that amount, 298 kilograms tested positive for BFR. The graph on my right shows a comparison of the work that I did with other countries that have done the same work. Next slide. So the plastics that were infused with BFR were taken through analysis using the X-ray fluorescence analysis. And some of the plastics that we analyzed had levels of bromine in them, showing that those plastics that tested positive for BFR, which is brominated flame retardant, contain bromine. The one on your right shows a significant amount of bromine in electric lamps. Next slide, please. So that's the other plastics from other electronic equipment that had also other elements in them. Next slide, please. So the plastics that did not test positive for BFR was taken to EMPA laboratory in Switzerland to test for BFRs, and the results came back all negative. Mostly all the results were below the recommended values. Next slide. Oh, this is my slide. So in conclusion, the total number of plastics that were worked on had this value, and then we had these trace metals in all the plastics that had BFRs in them, and all these metals are all additives, plastic additives that are added to the plastics during manufacturing. And then the BFR-free plastics that were tested here and then samples sent to the lab showed that the method that was used was very compatible It's a confirmation of the efficacy of the density separation technique that was developed by EMPA. Next slide, please. Next slide, please. So my recommendation, I recommend that there should be an establishment of a suitable reciprocal storage or disposal of BFR plastic containing debomination pre-treatment laboratories for removal of BFR plastics. And I'm happy to say that Ghana is having something like that put up by the Ministry of Environment. Next slide. So my acknowledgement. Next slide. This is the slide I sent. Thank you very much for your attention. This is not a slide.
Thank you, Gladys, for this very interesting presentation. So is there any clarificatory question for Gladys? I don't see any. Okay, so we have a few minutes before the session is closed. I don't know if there is any question from the audience, either from Zoom or from your application. Maybe I should ask Gladys about, I saw that there is a graph with differentiation between your study and other study results in terms of different plastics that you found. How do you comment on this? Is it a different sample that you used and with different devices, or what is your comment on that?
Oh, okay. They also did this a similar work like what I did, but the amount of samples that were used were a bit different. So comparing it with some way, but just to know that some other countries have also done the same thing.
Okay, thank you. Thank you, Gladys. And I also have a question for Dominic. I understand that, well, you translated the carbon footprint into money, right? In order to somehow take into account different criteria in order to optimize your reverse logistics network.
Yes.
Did you consider of running something, a different methodology like goal programming or multi-objective linear programming for this problem that you defined?
So MILP is already in the Any Logistics software. So that up until the economic point, there we weighed up the carbon, the carbon emissions and the FCI, and all of that was weighed up until that point. And then as a final check, then we did the carbon cost optimization. But as a result, MILP was built into the network.
And I don't know, you mapped all the reverse logistics network in South Africa. Okay, and if you could add an extra node in your reverse logistics network, would it be in order to further optimize, to further decrease the cost or further decrease the environmental impact? What do you think would be needed? Another dismantler, another end-of-life treatment facility? What would be it?
So at this stage, that's quite a tricky question to answer. So at this stage, what we did, for example, is we determined, so from our collection centers, we know the flow of material that we would be getting in. We know where they are suited geographically. So that allowed us to determine the optimal number of dismantling facilities, which in the first year was 4. What we then did is we ran through this year by year, and we determined where is the optimal location to keep adding these facilities. So that is dependent on economy of scale as well. And then from there, we took where those facilities are based geographically, and then where our customers sit to determine where the optimal location is for the process facility. So in terms of the optimization problem, it is optimal from that perspective. However, what we can now start looking at is different configurations. So for example, in the model that I've developed now, we have pre-treatment at our process facility, and at the dismantling facilities, we're simply just taking the batteries out. What we can now look at is different configurations. So can we, for example, perform pre-treatment at the dismantling facilities? And what happens there is you might have an increase in your equipment costs, but you have lower station costs. Or could we, for example, not have a process facility and just pre-treat the e-waste and the batteries, get our black mass and sell black mass off instead? So I don't think it's necessarily a question of adding nodes or changing the structure, but just looking at how that structure acts according to each other. Yeah, I'm not sure if that answers your question.
Yeah, thank you. It is super interesting, your work, and I will definitely go into it from the proceedings. Thank you.
Thank you very much.
Okay, so I don't know if there is any more questions. Yes, I get a message from Federico that do not forget to vote for your most interesting presentation, and yeah, you can see in the chat, you can see the link where you can find the poll, and you need to connect to session 2J. This is our session, so you could go to the link and submit your preference. So if there is no more question, I would like to thank you all 5 presenters actually, for these 6 very interesting presentations. Thank you for your engagement to the session, and I hope you enjoyed. Thanks a lot.